Hello, my name is Mr. Brash, and welcome to another one of my videos. This cute little fellow over here is Mr. Squirrel, and he likes to join me on my lessons. Now, if you've seen any of my videos before, they're a little bit lengthy, about anywhere from 10 to 16 minutes long when I can. And as we get more complex, they're going to get longer. So here we are in Graphing Parabolas Part 3. Now, because this is Part 3 and I'm dealing with vertex form, this is going to be a little bit longer, and there's going to be more than just one example. If you haven't seen my previous Graphing Parabolas videos, or you're not really sure on how to graph a parabola, you might want to go and check out those other videos first, or check out some Khan Academy videos, or what have you. We're going to be taking a look at graphing quadratics that take this form. It's known as vertex form. It's also known as turning point form, and I've also seen it called square form, simply because of the square on it. This is what it looks like. We get an A, which I like to call, and some other people in textbooks or whatever call it the amplitude. It gives us our concavity, whether it opens up or down, and this sort of thing. The H, I like to think of that as my horizontal placement. That is the X value of the vertex. And like I said, horizontal placement because it's an H. It depends on what you like to think of it as. The K is the vertical. And what I'll do sometimes, especially when I'm teaching it in class, is I'll spell vertical with a K instead of a C in order to make people understand that that's the up and down. So that's the Y value of the vertex. And what I'd like to know is, what other information does vertex form or turning point form actually give us? Obviously, it gives us the vertex. The vertex is going to be made up of that H and that K. And we have to be a little bit cautious because the X minus H can be a crutch for a few people. And we're going to see an example right now on the right-hand side. If we are asking, what information can I get from this particular equation? Immediately I can get the concavity. So right away, I know that it is concave down. That negative on there tells me that my parabola will be opening downward. Just like this. So I know that it is concave down. Concave down. I also know that because my A value, or my amplitude, is a value above 1, and what I mean by that is bigger than 1. 1.1 is still bigger than 1. We've got a 2 here. That means it's going to be twice as tall as it normally is. So that is a vertical stretch. I already know that there's a dilation involved here. A vertical stretch, and I'm going to put 2 times taller. 2 times taller. And which means it's also going to be thinner. I can get the vertex. We know that right away. And this is where I was sort of talking about that H value with that negative. It's really crucial that we take a look and understand what's going on here with my vertex. My vertex is not at negative 3. This is X minus H, and so the H is just a straight 3. If I ended up with X plus 3, that means we had a negative times a negative. I know my K value is what fills in the rest of the vertex, and so my vertex here is at 3, negative 5 for this particular equation. But what else can we get? Is there anything else that I can get from vertex form? Actually, I can get the y-intercept. Not exactly a huge piece of information, but if you're ever looking for another point on the graph, it is something that you can get. So I would plug in 0 for my x, and I would do the math on it, right? So let me just fill that in. Just kind of bring this over here, and we get 0 minus 3, that's negative 3. Negative 3 squared is 9. So this is negative 2 times 9 minus 5. And we get negative 2 times 9 is negative 18. Negative 18 minus 5. The y-intercept for this is negative 23. All right, negative 23 is the y-intercept. Now in the same vein, so what I did there was I put in 0 for my x. What if we put in 0 for our y? What if I actually looked for my x-intercepts? You're not always going to have them. And I'm going to put the S in brackets because you can have 1, you can have none, you can have 2. Let's visualize this parabola. We know it is opening downward. We also know that due to the vertex, it is below the x-axis. We don't need to actually draw out that full parabola, but I know just from the fact that it is concave down, opening downward, and the vertex is at -5 on the y-axis, so 3, -5 down here, I can visualize that it's going to go like this. Yeah, it'll be taller, whatever, but I know that I have no x-intercepts. So here I would say no x-intercepts, or some people say no real roots. Really just depends on who you're talking to. So I have no intercepts here. I don't even need to do the algebra on it. If I tried to do the algebra on it, we would end up trying to take the square root of a negative number, which is too hard to do. Let me show you that right now. So if I were to actually put 0 in for the y value and throw in the rest of the equation here, our job is to isolate x. So I'm going to add 5 on both sides. So I get 5 on this side. And now what I need to do is I need to divide by that -2 on both sides. And when I do 5 divided by -2, I get, -5/2, or just some decimal value, who cares? And when I get to this spot, I would try to take the square root of both sides, but I can't because of that negative. And because there's that unfortunate situation, we'd have an imaginary number. If you know anything about negative square roots or square roots of negative numbers, you end up with I, which is an imaginary number, but I can just say, therefore, there are no real roots or no zeros, no real roots or zeros. So we can get quite a bit from vertex form. It's almost more handy than factored form in some ways, right? All right, let's take a look at an example. Oh, actually, no, I'm going to ask you this question here real quick. How many points do we need to actually draw a parabola? What would be the minimum number of points that we would need? We really only need 3. All right, we need the vertex, and then we need 2 other points. But do we actually need 2 others? We know that a parabola is symmetrical. And so we can sort of cheat and say we don't really need 3 points, we just need 2 points. The vertex is the definite. You absolutely 100% without question need the vertex. But if you can find another point somewhere on the parabola, maybe I'll go over here and I'll just say I find this point here. I can immediately know, because parabolas are symmetric, I know that on the other side of the vertex, I'm going to have a spot at the same height. It creates something called a step pattern. Some people call a step pattern. But essentially, if I go a certain number to the left and find a spot, I can go that same distance to the right and find the spot. You don't have to go to the left. You can pick any side you want. But let's just pretend I go, 1, 2, 3 to the right, and I find that y value. If I go 1, 2, 3 to the left, it'll have the same y value. And that's fantastic. So vertex form is super handy for getting quick drawings of a parabola. All right, now I'm going to ask you about an example. And as with any of my videos, I highly recommend that you pause it and try it out for yourself. But what information can we get, and then can we sketch this parabola? So we've been asked to determine the vertex. Okay, so the vertex is really easy to obtain. It's my h and my k. Now in this case, remember that it's supposed to be x minus h. So I must have a -2 for my h in order for this to be an x plus 2. So my vertex is at -2 for the x value. I know my k value is the 9. I can start graphing it right away if I wanted to right now, simply because I've got the vertex, but I'm going to hold off on that. It asks us to find the zeros. Okay, I didn't show necessarily fully what happens when you do get zeros, so we're going to attempt to get zeros in this one. We can also visualize it and ask ourselves, will I have zeros? It opens downward, it is concave down, and I was asked to find the concavity, so I know now that it is concave down. And it is above the x-axis because my k value is a 9, so yes, I will have zeros. So I've plugged 0 in for the y value. Let's subtract 9 on both sides. Then we're going to have to divide 9 by 0.25. And that gives us a value of 36. A negative and a negative make positive. So I've got positive 36, and I'm left with x plus 2 squared. And now I will square root both sides. When I square root that, I get a positive and a -6 as an answer, and x plus 2 on the right. So I know now that either 6 equals x plus 2 or -6 equals x plus 2. And I have 4 as one of my zeros, and I have -8 as the other 0. I have 3 points, the vertex and the 2 zeros. I could graph this immediately. It then asks me to find the y-intercept. So I showed you before how to find the y-intercept. You just plug 0 in for x. So I plug 0 in for x. So that's 2 squared. 2 squared is 4. A quarter of 4 is 1. That's a -1, so it's going to be at 8. My y-intercept will be at 8. I did that really quickly in my head, but you would obviously plug in a value and show your work for your teacher. Just trying to make this video as quick as possible. So I've got my important information. Let's create this graph with a scale of 1. So 1, 2, 3, 4, 5, 6, etc. Hopefully you have graph paper, or you could print out your own grids. And I know my problem is going to be in quadrant 2 because of what the vertex stated. The vertex stated that I'm at -2. -2, there we go. And I believe 9? Yes, -2, 9. So -2 and 9 is where I'll plop my vertex. I know my y-intercept was 8. And actually, because I know my y-intercept was 8, I don't really need the zeros to continue drawing my parabola. I know that that's 2 squares to the right. If I go 2 squares to the left, I know my parabola should hit this point because parabolas are symmetrical. Now, that being said, I do know my zeros were at 4 and -8. 4, 5, 6, 7, 8. And now I have more than enough information to sketch out my parabola. Remember to connect your dots with a curve and not straight lines. And if you've seen any of my previous videos, you know how wonderful I am at drawing and just how beautiful my lines are. Now I have a drawing or sketch of that particular quadratic that we had up here for the question. So I got my vertex, my y-intercept, and my zeros, and I was able to plot that down. Let's take a look at one more example. Of course, you could stop the video here if you wanted to, but I just thought because this topic is maybe a little bit more difficult for some people, I'd give one more example. Here we've been asked to sketch this parabola. We know that it is 3 times taller than our normal everyday parabolas that we would deal with, like y equals x squared. And I also know where my vertex is. My vertex is going to be at 5, 1. And we could graph that right now if we wanted to. Let's just go with 1, 2, 3, 4, 5. So I know that I'm going to be at 5, 1. You know, you would put a proper scale on your graph for your teacher, please. I know it's going to be opening up, and I know it's going to be 3 times taller. So do I really need to go through the trouble of finding more points algebraically? You know, find the x-intercepts if you want to, find the y-intercept if you want to. Now this parabola opens upward and I'm already above the x-axis. So I'm not able to get the zeros. So what if the y value is way off the graph? You know, the y-intercept could be way up here. As a matter of fact, if I plug 0 in for x, I get 25 times 3, which is 75, plus 1, which is 76. My y-intercept is at 76, way, way, way off the graph. So how do we obtain 2 more points? It's not as hard as it sounds. The normal parent function, which I'll draw in purple, the normal parent function has a vertex at the origin, and then if I go 1 to the right, I move 1 up, because I will be squaring an x of 1, which gives me a y value of 1. And if I move to the left by 1, I go up by 1. That's just the natural progression of the parent function. So what if I go 1 to the right of this particular function? If I go 1 to the right of this one, I'm supposed to be going 3 times higher than I normally would. Normally, I go up a distance of 1. Now, instead of going up a distance of 1, I'll go up a distance of 3. 1, 2, 3, because I'm 3 times taller than I would normally be. And you could always test that with a table of values. Put 6 as an x value into this equation. 6 minus 5 is 1. 1 squared is 1. 1 times 3 is 3, and 3 plus 1 is 4, a y value of 1, 2, 3, 4. So I've got my second point. Parabolas are symmetrical, and I can now connect my dots. And because this parabola is 3 times taller than the normal parent function, you can see that my y-intercept would be way up at 76, like I mentioned before. And now I have my sketch of my parabola. It is important too to notice that the question said sketch, so I don't have to be 100% accurate, and 3 points are enough to get this parabola down on the screen. I'm just going to finish this drawing by filling in my other parabola, which is the parent function, and labeling it in order to have a reference parabola for you. Okay, so this parabola is y equals x squared, whereas the yellow parabola is my function over here. I'll just label that as function 1, and I'll give this the label of 1, and there we go. All right, so that was graphing parabolas from Vertex form. Again, that's part 3 of my series for these graphing. I've got a lot of videos on parabolas and quadratics. I suggest you do check them out. If you don't like my videos, you can check out Khan Academy or anybody else's videos on these topics. And as always, feel free to leave a comment, give me a thumbs up. If you're going to give me a thumbs down, I suggest you also leave me a comment to let me know why you're giving me the thumbs down so that I can improve my videos for further lessons. And if you're so inclined, you can subscribe to my channel, and that would be greatly appreciated. My name is Mr. Brash. This cutie over here is Mr. Squirrel. He approves this video, and hopefully I'll see you next time.